Okay, welcome everyone to our last Water at Wayne seminar for this semester. I want to thank everyone that took their time to be in the meeting today. I'd like to ask everyone to remain muted throughout the event and to keep the chats and the comments in the chat box. We will be taking questions through that. And since we have everyone joining, we just wait a minute or two before we get started. Okay, so we can go ahead and get started. And I'd like to introduce our speaker for today, Dr. Jeff Hu. He's an environmental engineering postdoctoral research fellow. And I personally got to know Dr. Hu through my work with Dr. Miller in civil and environmental engineering. And it was really nice for me to meet Dr. Hu and to hear about his work. And he's currently doing research understanding water resource issues. His current research is funded jointly through the Cleveland Water Alliance and NOAA SIGLAR out in Ann Arbor, with a focus on advanced cross-disciplinary water research using a variety of in situ and remote sensing technologies. He hopes to share his findings with diverse stakeholders and contribute to ongoing efforts to protect Great Lakes water resources. His past work focused on riparian zone monitoring using remote sensing and GIS, and green infrastructure performance modeling using real-time environmental sensors. Jeff obtained his PhD in water resource engineering from the State University of New York, College of Environmental Science and Forestry, and master's and bachelor's in environmental engineering from Drexel University. So it's really great to have him speak to us about his work. I personally am a physiologist and he's an environmental engineering, so I really like the interdisciplinary nature of the work that he's doing, and really glad to have you here, Dr. Hu, and the floor is yours.
Thank you so much, Adrian. I have been a big fan of Water at Wayne, so I'm really honored to speak here and present my work. What I'm presenting to you today is my postdoc work since last April on a variety of in situ IoT sensors. Let me get right into this. So just to lay some groundwork or the background in my talk here today, I will mainly focus on water resource monitoring and just some classic examples of water resource monitoring you would probably already know. These are some quick examples. On the left is in the water level sensors. These are very popular for USGS to monitor water level using this kind of setup. It costs around $4,000. So the price is fairly high, and it requires kind of graduate degree to operate these sensors as well. And then on the right is water quality sensor. This is also kind of industrial standard, our go-to. Once the YSI sound, probably a lot of you already know, that costs around $12,000 to measure a variety of parameters. So just keep these price in mind after we go forward here. So one of the key challenge of using these classic approach is it's really, really hard to scale up. And we do know a lot of these environmental parameters or phenomena that we care about, such as the hypoxia on the top left here, denoted by the water temperature, and then inside the Lake Erie, for example, the HAB patterns, this is from the HAB grab research actually, shows that the phenomenon that we are looking at are quite spatially variable. So it's really important for us to measure the spatial variability of these phenomena. But with the classic approach that I have shown earlier, it's really hard to scale up because the cost is really a big barrier for us to install a whole variety of sensors across the Lake Erie, for example. In the graph down below, this is what we have right now. And you can see it doesn't really quite get the entire spatial pattern there. So that's something that's really kind of a challenge for us. So that's within the lake itself. But if we look at land-based measurements, for example, water level, USGS measures both the flow and the water level across the nation. So on this graph, you can see it's pretty great. USGS maintains tremendous amount of gauges across the nation. But when we zoom in into, for example, individual watershed, for example, the Ohio, this is the Old Woman Creek watershed, and on the right is the near Detroit. I highlighted my apologies for my hand draw sketch here, but I highlighted the Huron River watershed. And you can see the amount of gauge is really lacking. In the case of Old Woman Creek, we only have one gauge there for us to understand the flow there. So it's really hard to understand, and also because of the high price of these sensors, it's really limiting our ability to deploy a variety of them across large spatial scales to understand complex patterns. The other challenge associated with the cost itself is also the access. So right now, because the sensors are so expensive, only universities or government agencies can be able to purchase them and operate them. And citizen science groups or the general public often have limited access to these simply because they are so expensive, and it's really hard to imagine anyone, a general citizen can purchase a sensor to measure environmental quality in their backyard, for example. That's just not possible with that price tag. And lastly, of course, it's really costly to repair. And if you accidentally broke one of these sensors, it also costs a lot of money to repair them as well, or exchange them. So these are the main challenges. And you might be asking, how exactly do we reduce the cost? Is this even possible to do? Well, before I get into that, I'm going to introduce two technologies or innovations that has happened recently or very recently in the technology world. The first is the introduction of a brand new kind of networking technology, and it's called LoRaWAN. So this is very different from the cellular network or the Wi-Fi network you probably is familiar with. It is relies on a very low bandwidth of transmission, so it can transmit kilobytes per second of data, which is very ideal for environmental sensors, because simply we do not need gigabytes of data or gigabyte per second speed to transmit water level. So LoRa network is very ideal for that purpose. And then the other benefit of using LoRa is it uses very, very little amount of power. So comparing to Wi-Fi or cellular, you would need a very large battery to operate because you need so much power to send that data. With LoRa, you just need a very small, like a 3-volt battery, and you can be able to transmit data very easily. So this really give us ability to improve upon our classic approach and innovate. And I will show you examples of how that looks like in the next examples. And at the same time in the technology world, there's another innovation you might already know, very familiar with. That is the general trend of miniaturization. So downsizing the component, but doing the same thing that we are trying to do. So on the top, you can see example of computer that can occupy a huge desk to transforming all the way down to a computer that's can fit in your hand, and you can basically do and accomplish the same tasks using all of these. But the main goal is to kind of downsize and also reduce the cost to accomplish the same task. So with this idea of miniaturization, it enables a lot of different possibilities. So that in the telecommunication world, you probably already know the phone size is constantly downgrading. Now can be able to fit our pocket. And then in the remote sensing world, the same technology or the trend is also being applied. We have sensors that are bigger than a house. It can now be reduced down to fit in your hand. A satellite you can shoot up in the sky and be able to take images. So this trend or technology innovation has been really fundamental in driving the different thinking that we have in variety of different fields. And this is no different for environmental monitoring. And here I'm bringing a pop culture example. This is the famous movie Twister that was made decades ago, I believe. And this really emphasized that the downsizing of the environmental sensors has already begun a long time ago. And it's really kind of reducing. Here I'm showing you example of monitoring hurricane and the variety of, or tornado in this case, and reducing the size of this sensor into a very small sensor that you can be able to send up into tornado itself to be able to have a better understanding of the tornado structure inside of it. So the environmental monitoring is really taking up the benefit of this new innovation technology trend and to improve up on the the size of the sensors. And by reducing the size, we can now be able to make these sensors more affordable so that everyone can be able to access these sensors. So here I'm showing you an example over the years for water level sensors alone. there has been reduction in the sensor itself using different technologies, and now we can be able to substantially cut down the cost from $3,000 to now $100 to measure the same thing, water level parameter. So it's hard to not talk about numbers when I'm trying to explain to you how much cost are we actually saving here. So I am showing you in this graph a very quick example of how much money you are looking at if you are just measuring water level, comparing the classic example to the more affordable example. So here, the classic example, I use a water level sensor that's a little bit more expensive, and then communicate through a cellular network, which has been the classic approach, and then connect to a cloud data platform. And then for the affordable approach, I added on here the example of a $200 sensor connect to using LoRaWAN. This is where a lot of the savings has been, is reducing the annual cost down to just $1 to use the LoRaWAN network and then communicate through a cloud data platform. So at the end, you can see that the cost has been reduced substantially by almost 75%. And for that first year, you're looking at around $2,000 of saving. And what this saving can do is you can essentially having more of these sensors developed across or deployed across large areas for you to measure spatial variables and have a better understanding of the parameters that you are looking at. So this is where I'm going to talk to you about the affordable sensor kits that we have worked with some examples. So with close collaboration with Liminotech, we have developed this system or this kit that essentially use 3 different main ingredients, if you will. The first is the low-cost sensors. As I mentioned, these are some of the examples I will talk about in the next slide. And we also utilize the LoRaWAN network, as well as combining the real data reporting platform, which enables this really kind of fundamental technology that we are trying to develop. That's the low cost, low power, yet real-time sensors. And the great thing about the sensors themselves is all of these sensors you're looking at up here are they only have a 3-volt battery inside of them. So they are really small in terms of size. And the batteries can last for 5 years or more, depending on the weather or the location. But point being that you do not need to periodically change the battery anymore. You just need to deploy it, and it will last for years to come. And then the other is the cost part, which these sensors are less than $100 per unit and cost around $1 per year for collection. That's recording at 5-minute interval, which is a lot of data, but still it costs very little money to use LoRaWAN. So here are what we utilized for this specific sensor kit. It measures the air temperature, relative humidity, and also water level using ultrasonic, as well as water temperature. And these are the different price tags that are associated with these. And we improved up on this design. So basically, outfitting these sensors with different enclosures, as well as solar radiation shield you're seeing here on the left, to give us better measurement. But still, you can see even with the improved design, so with the casings, it's still less than $100 per sensor itself. And here shows you an example of the real-time data dashboard. Here we utilize the UBDOTs as one of the example, but obviously there are a variety of options out there for you to use. And we also have the capability to connect to the different real-time data platform as well from the sensors. And these plots, you can graph these and they can be able to stream real-time data. So you can basically open up these charts, and every time when a new data point comes in, the chart will refresh itself, which is great for real-time data management. So so far we are fortunate enough to collaborate with a variety of organizations across Lake St. Clair and Lake Erie area to deploy these sensor kits to test both the reliability and also the capability of these sensor kits. And we were able to deploy these in a variety of environments. So you can see in the Old Woman Creek in Ohio, it was deployed in a river stream environment, where at the University of Toledo, Lake Erie, this was deployed at the lake shoreline environment. And in Ann Arbor, we deploy these mainly in pond conditions. And also at Wayne State, when we collaborate with Wayne State, we were able to deploy these sensors in marsh environment, as well as vernal pool environment. And I will also show you pictures of these since it's hard to visualize the setups here. So there's a lot of photos in this slide. I will walk you through each one of these just to better show you the environment and also the sensor setup for these. So in Ann Arbor, as I mentioned before, in the pond environment, right outside of Liminal Tech building, we were able to deploy both the air temperature and humidity, as well as water level sensors. So these are example photos of that. There is a pond to the north of Ann Arbor where we were able to kind of modify the sensor themselves a little bit and strap basically 3 temperature strings together to form a temperature string that can measure the water temperature at different depths in a pond. And we strap that to a smart buoy and throw in the pond to measure that. So that's a modification for the affordable sensor kit. At Old Woman Creek, this is a different environment. So in the river environment, we were able to mount these kits on bridge sites, and we were able to measure the water level from the bridge themselves. Lake Erie, as I mentioned before, at the shoreline environment. So this is right along the shoreline of Lake Erie. We were able to mount the sensors to measure the water level change in Lake Erie at that location. At Lake St. Clair Metro Park, we were able to deploy these sensors at variety of locations across the metro park to measure the water level, water temperature change at variety of locations, both in the marsh but also in the lake as well. And at Palmer Park, which these sensors were deployed just yesterday, just deployed yesterday afternoon, and these were deployed in a vernal pool environment. So these are kind of very forested area. So it's quite different from the other ones we have so far. So it's really interesting to see how the data comes in for that site. So with all the deployment done, naturally the next question is, what is the quality of the data that are coming in? Can we really be able to trust these data? These are very cheap sensors. One of the natural question that arise is, are these cheap sensors associated with bad quality data? Well, let me tell you with what we find out here. So for the water level sensors, this is the graph that we made for the sensor that we deploy outside of Limnotech. And we basically mounted a plate that is right underneath the water level sensor. So technically, the water level sensor should be reading exactly the same water level at all times. So here you can see the graph down below. This is the general time series. There are some very wild fluctuations of the water level readings, and I mean the distance readings, and these were due to special weather phenomena that we observed, such as storm events. But generally, you can see that when we zoom in on a section, we can see the reading is between 490 and 493. And 490 is the actual target of the distance between the water level sensor and the plate itself. So it's reasonably well reading. So it's off by 3 millimeters. And one interesting thing that we observed is for this ultrasonic water level sensor, it has this fluctuation of this pattern that's generally daily pattern, and that's associated with the temperature fluctuation by the sun. So when the sun is shining onto the sensor, the readings are off. And that's one of the main reasons we applied a temperature shielding. If you look really hard into this photo, you can see we modified that sensor to put a temperature shielding to mediate that effect. So that's one critical thing that we have found for that. And on the right, you can see this is another way we measure the accuracy of the water level. This happened at Old Woman Creek, where we compared a USGS quality sensor, as you can see highlighted in color red, and we mount a water level sensor, the affordable version, right next to them to see what are the readings, how different they are. So as you can see on the top, this is the time series plot for water level. You can see the patterns match up quite well, except some areas you can see some deviations from them. So I took a difference between the sensors, and as you can see, majority of the readings indicates that the water level for the affordable sensor is off by within 0.05 feet. So that really gives us the confidence in terms of how much can we trust the water level readings from these affordable sensors. So for the air temperature sensors, we were also able to do very similar comparisons as well. And here you are seeing an example of comparison. If you can focus on this plot on the top here, the green dot is where we mounted the affordable air temperature sensor. And then the orange is where the NOAA air temperature sensor is at a nearby Ann Arbor airport. And in between them is about 0.62 miles distance. So we were able to compare first the time series of the pattern. You can see the pattern of the air temperature measured match up fairly well, with some exceptions in terms of very lower, some underestimation of the air temperature there for the affordable sensor. And if we zoom into here, into one strip of this, we can see that there is some kind of phenomenon that's impacting the reading for the lower end of the air temperature. And this is mainly due to the fact that the NOAA air temperature were mounted above grass area, while the air temperature we mounted at Limnotech were above water bodies, so a pond area. And that really drives the difference for these lower values for the NOAA sensors. But in general, when we compare these two sensors, we can see that the general difference is within 2 degrees Celsius for the affordable air temperature sensor, except these systematic lower value for the NOAA temperature sensors. So that again gave us the confidence to utilize these sensors and also able to quantify the accuracy of these measurements. And last but not least, the water temperature sensors, we're also doing similar accuracy quantifications as well. This is a setup that I am currently in progress of measuring these. So we basically mount a affordable water temperature sensor. You can see that's feeding from the left here, and attach that right next to the YSI water temperature sensor to compare the readings. And that result is upcoming. Yep. So with the accuracy of the measurements measured, now we can be able to talk about exactly how capable are these sensors in the field. So the first capability I would like to mention is the amount of range, the signal for the sensor themselves to be able to travel. And these two I selected for sites that we collaborate with Wayne State University. And you can really see that the red triangle, it indicates where the sites are. And then the circle are where the towers are for the different LoRaWAN signal transmission towers. And you can see that for the Lake St. Clair Metro Park, we can be able to have signal travel 5 miles out to be able to transmit that data. And also for the Palmer Park, we will also be able to transmit greater than 6 miles in this case to transmit the data. So this really shows the ability for LoRaWAN, which I forgot to mention earlier, is that it can be able to transmit really, really far range. And it really benefits us in terms of, saving the cost to building up these towers ourselves, or you have to building up multiple towers or to be able to transmit data. The other capability I would like to mention is the longevity of the battery and the sensor itself. And here I'm showing you for the water level sensor, we mounted at Old Woman Creek to measure water level. This is the longest sensor that we've deployed. That's why I'm showing you this graph for the battery. And you can see that one of the longest deployed sensor in red here, it has been lasted for a little bit about 2 years, a year for that one, and then it's also keeps going on onward. And for the Ann Arbor sensors, these are kind of also longer time period deployment, and you can see the battery themselves have decreased battery in the winter, but they do recover in the summer. So we do see this increasing pattern in the summer for the battery. And that also goes to show that the reliability of the battery themselves are pretty good. And the signal that are sending out as well are pretty reliable, simply because they use very little amount of power to transmit the data. So with the capabilities aside, I would like to show you what can we do with the data that are measured from these water level sensors. In particular, just an example. So here I'm showing you a graph that I extracted from the Old Woman Creek water level measurements. And this just to show you example of how powerful it is to have these water level measurements at different locations so that we can measure different phenomena, hydrologic phenomena. So here I've selected a fairly large rainfall event that happened back in February, so earlier this year. And this rainfall have caused substantial water level increase at all of the 3 sites that we deploy these water level sensors. And what's really interesting from this graph is that you can see as the water travels down from upstream to downstream, the peaking of the water level happens at different time. So this is very interesting in the sense that we can now be able to quantify how fast that water moved downstream. And if we can be able to incorporate water quality data along with this, we can now be able to understand how fast, for example, a plume of polluted water is moving downstream in this stream itself. So this really enables us to be able to capture that spatial hydrologic phenomenon and also quantify that as well, how fast the water is moving. And this is really great in the sense that with the previous setup that I mentioned before with a classic approach, it's really not possible to do this because we will be looking at tremendous amount of money for one to be able to do this. But also we also would need to constantly be changing batteries as well for the classic setup as well for this. The other really interesting hydrologic phenomenon from this graph is you can see that the amount of decrease, so in between the storm events, the amount of receding of that water level also is different at the 3 different sites. And you might be asking, why is that? Well, if you have been to this site, you would see that the upstream is a very steep valley. So the cross section of the slope of the channel is very high at the upstream. While you go downstream, then the slope of the channel opens up, where eventually at the mouth of the river, it opens up as a actually a wetland area. So this simple demonstration here showing the 3 different changes in water level also matches up with the hydrologic underground channel geometry as well. So this is also very useful in terms of quantifying that water level increase and how that associated with the channel geometry. And another example I would like to show you at the Lake Sinclair Metro Park. This is some of the preliminary data that we've had. I only took a segment of the data that we have so far. And this also is a comparison of water level sensor that we had between the affordable sensor and the kind of more expensive sensor that NOAA has near city of Detroit. So if you focus on this map down here, the red dot indicates where we mounted the water level sensor, the affordable one, in Lake Sinclair. And then the blue one is where the NOAA water level sensor is. And you can see the general pattern also matches up pretty well for between the 2 sensors. One interesting thing I would like to point out is for the sensor that we mounted at the outlet of the marsh, which is inside Lake Sinclair, you can see a lot of these up and down fluctuations in the red lines here. And that is mainly due to the wave actions of the lake water, where the NOAA sensors are mounted, inside a stilling well where the water is fairly calm for that. So that is one comparison example. And on the right, this is comparing the sensor at the mouth of the marsh to within the marsh itself. So you can see the red dot here indicates at the mouth of the marsh, so that's inside Lake Sinclair. And the green dot indicates inside the marsh what the water level is. And as you can see, the general pattern matches up pretty well. But again, you can see that up and down fluctuation of the red line, which is the lake water level. So if we quickly zoom in on one segment of this, we can see that fluctuation much more clearly in terms of how the lake water is changing rapidly, or the wave action comparing to inside the marsh, where the water is fairly calm condition. And this can be utilized further down the road in terms of how the marsh is protecting organisms and forming habitats by preventing or also mediating the wave actions from the lake itself. So that's something that could be interesting to compare further. So here is another example that I put in here. I promised a lot of examples in here. So this is the last one for the marsh example, or I believe this is the last example that I have for the data. And this is at the same Lake St. Clair Metro Park. And here what I plotted are 3 different parameters. One is the rainfall, which is from a rain gauge nearby to the park itself. And also the water level I plotted. This is comparing the water level inside the marsh I'm showing down here to the south. So to the left of the park itself. And that's associated with the brighter green color. We also were able to mount a darker green color dot here. This is another water level sensor that we were able to measure the water level on the larger marsh to the north of the park. So when we compare these 2 values, you can clearly see sometimes these patterns matches up fairly well, but sometimes it does not, where you see kind of in the December time range. And this is partially could be due to the freezing temperature conditions, that it could be simply just measuring the snowfall, because there's the water is not present at that time. One interesting though I would like to point out is you can see in this graph when the rainfall falls onto this area, it's generally associated with increase in the water level for the later rainfall events, as you can see. But there has been a large rainfall event where you can see kind of happens around December 25th. This did not result into a increase in water level. And this was also quite interesting because you can see that rain falling onto the area actually resulted in the melting of the water in the park. So it's just quite interesting in terms of how we can be able to understand the water level fluctuation and the spatial variations of the hydrologic conditions in these wetlands through the deployment of these sensors. And now we can be able to really tease out what is causing the water level change and what are the different possible reasons that we can explain that phenomenon. So in summary, I would like to especially mention the variety of different benefits to affordable approach to measure water resource and also environmental resource in general. It's really kind of this seesaw action here. So with the affordable approach, we can now be able to increase the redundancy of our monitoring network and also increase the density of the measurement. And one other great thing about this is we can now be able to provide more access to these sensors to more folks who are interested in these, and not just limiting them to government agencies or university groups. The one important thing I would like to mention is that it's not really a competition, I would say. Even though I show this seesaw action here, it's really the affordable sensors can be able to enable this brand new realm of environmental monitoring with more affordable approach. So by that, what do I mean is essentially this graph here, where we have the affordable approach and the classic approach. They differ by cost and the amount of accuracy. So when you are choosing a sensor, it really depends on, these two critical parameters. One is your budget limit, and then the other, of course, is your accuracy limit. And where those two lines merge is, kind of the sweet spot, if you will, for you to select the approach for you to monitor water resource. And I've just quickly plotted some examples here. These are very brief, rudimentary examples, and they do not have to be where they are. I just simply give you an example here. But some of these examples I can talk about for this is, for extremely high stake situations such as, reservoir monitoring or some other, flooding measurements, things like that, that would require both high accuracy and high cost. That's understandably, you would definitely need the classic approach to spend thousands of dollars for one sensor to measure that parameter. But for spatial research, as I mentioned before, it could be somewhere in the middle between affordable approach or classic approach. So in that sense, you can, purchase a $1,000 equipment and then accompany that equipment with, a different variety of affordable sensors around it to be able to have a better understanding of the spatial pattern. And for citizen science groups, cost is definitely a very critical component to these programs, I would say. So I would, imagine one of the approach or preferred approach could be the affordable approach, as an example that I just simply put on here. With the other group that I want to mention is the concerned public group. These are, for example, if someone wanted to measure erosion or flooding in their backyard, they simply just wanted to see the trend of, the flooding or the water level increase, and they, wouldn't want to spend a lot of money. That's where the affordable approach really shines for that group in terms of, needing a lower accuracy and lower cost to be able to conduct that water resource monitoring. And I just wanted to show this simply because before the affordable approach is possible, it's really not possible for the groups, especially concerned public and citizens or community science groups, to be able to do this with a affordable, means. And I would like to reiterate here as well, if spatial monitoring or spatial understanding of the water resource phenomenon you are trying to understand is a critical concern, so your top priority, and you would want to, have a lot more sensors deployed, this is the savings that you are looking at. If you wanted to spend, if your budget is limiting you, you're definitely, the affordable approach is the way to go here. And the saving is substantial, as you can see. If you're approaching 10 units, it's $14,000 of saving, and then with 20 units, it's even larger saving. If you are, trying to do a larger spatial scale research. So this one last part, I just would like to reiterate as well. I did mention this before, which is with the classic approach, we are really limiting our capability to monitor environment or water resource to universities or municipalities where budgets are, fairly large comparing to citizen science groups or the general public. But with the affordable approach that we've developed, and also other examples that are ongoing, we can really open up this new environmental monitoring to even more diverse audience, such as citizen science groups and general public. And this would be great in terms, promoting science to everyone, in terms of motivating and be able to understand the water resource phenomena through monitoring. So this is, in conclusion, I am showing you some examples of deployment that I've showed before. We've so far also been able to share our knowledge with a variety of audiences and stakeholders, managers. We developed webinars as well as training videos. You can feel free to check these out. These are on YouTube, so readily available and accessible. And these basically walk you through exactly how you can put together these sensors yourself, and how you can connect these to the network and monitor different water resource parameters. And also, there is a upcoming workshop that I will be doing in Joint Aquatic Science meeting in Grand Rapids soon on this topic as well. So if you're interested in learning more about these sensors, I'll have these sensors with me for you to take a look. Sometime I know it's easier to actually have them in your hand to understand them. And I periodically, share some of my results on GitHub or Twitter. You can feel free to check those out as well. And with that, I would like to thank the various collaborations with variety of partners that we are fortunately enough to work with to enable all of these work. And I would encourage you to contact me for any kind of collaboration in terms of, whether installing these sensors or helping to understand how does these sensors work. And I would be happy to talk. My contact information is down below, especially my email is down there. And with that, any questions?
Thank you, Dr. Jeff Hu, for that really good talk on these technologies. We have time, maybe one question. We're pretty much out of time right now, but I would encourage everyone to email Dr. Hu at his email that he listed there about these technologies and how the deployment. We have one question from Jeff Ram. I wonder if you could install a water height sensor inside a sewer to determine flow rate by sensing the height of the water. and come.
Yeah, I think that's definitely possible. And you mentioned inside a sewer main, you said? Was that?
Yeah,
Okay, yeah. I think there needs to be some kind of a conversion for the geometry of the cross section for sure. But the water level can definitely, the sensor itself can be mounted in those conditions to be able to understand the flow.
all right. Well, once again, thanks a lot, Dr. Pu, for taking time to speak to us. If anyone else has questions for Dr. Pu, his email is there on the screen. I think this technology is great, as you know, not everything that is more expensive means it's better. It has to be well made. That's the thing that we're interested to give it. So I think this type of technology and its application has broad ranging use across the world to monitor all these things as climate factors become more of an issue, and all type of things are going on in the environment. Definitely need more of this. So thanks a lot for speaking to us, and we're collaborating with Dr. Pu. And please reach out to any of us if you really have some questions or collaborations that you'd like to express with Dr. Pu. I'm sure he's available for that. All right, thanks everyone. It was great having you for this semester of Healthy Urban Waters. This is our last one for this semester. I don't know if Jamie had anything else to add.
Yeah, I just wanted to mention, like Adrian said, this is our last Water at Wayne this semester. Thank you so much, everyone who was able to attend. I'll be sending out a recording following this event of this seminar. And then the other thing is I will be, if you're interested in finding out more about our Water at Wayne seminar, feel free to email me if you're not already on our Hue email list. But yeah, enjoy the rest of your semesters, everyone, or the rest of your years. And thank you again, Jeff, for speaking with us. We appreciate this presentation.
Thank you so much for having me.
Yep. Bye.